Hello there, my name is Jimena Garcia, and I have a guitar, and I also have this YouTube channel. While I was looking at said guitar, I realized I don't know how to play, and while desperately trying to play like a little cool little tune to convince myself that I'm just in the learning process, I was wondering, how did people even come up with the build and the spacing between the frets to produce the notes and pitch of the strings? And so, because I remember a certain math teacher saying how everything has math behind it, I just knew it was going to be something good. So I googled it real quick, and I found something called the Pythagoras fractions. I was like, hold on, isn't that the dude, the triangle dude? I was like, what does he have to do with guitar tuning and setup? And so after piquing my interest, I came to today's topic, which are what are the mathematical elements behind the frets and tuning of the guitar, and how does it work? A little late, I guess. Okay, so let's start off with looking at a guitar. There's a guitar. Yeah, anyways, here's the bridge. Here are the frets, which are the spacings in between the metal linings. And these are the tuning keys. And yeah, I was just looking at this and I said, who really even like came up with notes and the concept of tuning and all the setup of the guitar? Turns out Pythagoras was a musical guy and went crazy on this. Crazy like he figured out a lot of stuff, not like went insane. Well, maybe. But I don't know. Anyway, let's start off with some sound basics. Um so let's start off with the way we measure sound and notes, which is through their frequencies, which is the number of vibrations of a string in this case. That takes place each second, also known as oscillations. Higher frequency of a note gives us a higher note, and a low frequency would give us a lower note. And we measure frequency in the unit hertz. Now let's do a quick little example of how notes are displayed on a graph. Here is this remarkably humble graph, which I have labeled the y-coordinate in displacement per second, or per centimeter, I mean. And what I mean by displacement is how far the string would go up and down when plucked. So, when you pluck a string of the guitar, it's going to wiggle up and down and create sound waves, which on this graph should look a little familiar. Yes, a sine wave. Ta-da. Oh, and the x-axis is in seconds. So basically, when we're looking at this graph, we're going to be looking at the amount of cycles per second, or oscillations, which in this case, a whole cycle would take about 4 seconds. And because we can only see that in only 1 second, it's only about a fourth of a cycle was completed. So the frequency of this note would be about 1/4 hertz, which in reality is, a little low and probably not even audible. So, but anyway, let's keep this info for later and don't forget it, or else, I guess. Anyways, back to the guitar. Pythagoras was really like, you know what? I'm gonna take these 6 strings and play with them until I think they sound good. Since there used to not really be any set notes or name, he really just took what he had and experimented until they sounded good to him, and ended up creating every note in the Western chromatic scale. Western because main character things. No, just kidding. Because it's a scale mostly used in everything in the Western world. And the cool thing about this was that he figured out that each note that sounded best to him, when multiplied by some common ratio or denominator, gave him the adjacent note or the next note in the scale. So I thought it would be a cool idea to explain this cool fraction stuff. And let's start with looking at the scale. So now we have every note in the scale, and or at least in this scale, and including these weird little notes that have these little hashtags and these lowercase b's. And these are sharp and flat signs, which indicate that the note went either a half step higher, the hashtag or I guess sharp sign, or half a step lower, which equals the half sign. As for the seemingly missing like E sharp and F flat, I don't know how to explain that, so ignore it. Anyways, these notes are used constantly, and you might be thinking, well, if I managed to start at C, wouldn't there be a different note after that, after I went all the way around? The answer is no. The same note names are utilized, but they are not the same note because they would be a higher frequency or high or lower frequency. Now, when you go a complete cycle up, it would be called an octave, which would be this note doubled in frequency. Now for this example, let's look at the octave. What does an octave do to the beginning note? It doubles, so let's keep that information in mind for later. Now to solve for the common ratio, let's try to solve it with the first note, E. E being the top string and played open, which means without pressing on any frets, which would give us a higher note, is measured at 82 hertz, which is, I guess, cool. I don't know. So we have this note, which I'll call F of 0, which is also E. O because it's an open string and you're not pressing down anything. Times some common ratio that even Pythagoras didn't know, and I'll majestically call that R. Which equals the next note, f of 1, which would in the scale be f sharp. F of 1 because you would have to press on the first octave to get it. Now this would be the equation until you get to the next octave, which at E would be f of 12. Which would be f of 12. So if we were to solve for f of 2, we would say that f of 1 times the common ratio equals f of 2. Or we could say that f of 0 times ratio times the common ratio 2 times equals f of 2. Or we could say that f of 0 times the ratio squared equals f of 2. So we could also continue all the way for every single note until we reach the second octave. F of 12 equals R12 times f of 0. So now let's try to solve this. This might look scary because we have three unknowns, and so let's try to cut that out. Because we know that an octave would end up doubling f of 0 or E, we can say that f of 12 is going to be equal f of 0 times 12 because f of 12 is f of 0 doubled. So we could say that f of 12 would be equal to f of 0 times 2, and then equal to the rest, so R12 times f of 0. So we would divide on both sides by f of 0, which voila, they would both cancel out, and we would get 2 equals R12. Now, how do we get rid of this 12 sign? Well, similar to if it would be squared, we would take the square root of it, or I guess the 12th root. So now we get R equals about 1.0595. And because we're going to try to see if that is true, we should know that f of 12 is going to equal 1.0595 12 times 82, or f of 0 originally. That's what the frequency it was labeled at. So it should also equal 82 times 2. Do you know why? I hope you guys know. Because 82 doubled would be the result of an octave higher, which would also equal f of 12 times this common ratio that Pythagoras was talking about. And what do you know? We get 164, which also happens to be 82 times 2. Hooray! I hope you like this YouTube channel. Don't forget to like and subscribe. Yeah, that's it. I'm out. Oh, wait. Yeah. Alright. Have a good day, everyone.